Welcome to Cosmos and Dreams. Tonight, we explore the most mysterious places in the universe, black holes, where space and time themselves dissolve into something we can barely imagine. If the universe is your kind of bedtime story, subscribe before you drift off. Now get comfortable, close your eyes, and let science carry you to sleep. Opening meditation. Close your eyes. Let your body settle into whatever surface holds you now. Feel the weight of your limbs. Feel the slow, easy rise and fall of your chest. Each breath is a quiet rhythm, steady as the turning of the earth. Tonight, we are going to travel somewhere extraordinary. We are going to journey to the edge of the known universe, to the places where light itself cannot escape, where time bends and stretches like taffy pulled between invisible hands, where the laws of physics as we understand them reach their absolute limit and dissolve into mystery. We are going to explore black holes. But we will do it gently. We will do it slowly. We will begin with the simplest ideas, the earliest thoughts, and we will follow the long, winding river of human curiosity as it flows toward one of the most astonishing discoveries in the history of science. There is nothing to do right now but listen. Nothing to solve. Nothing to worry about. The universe is very large, and it has been here for nearly 14 billion years, and tonight it opens itself to you like a book, one quiet page at a time. Let your breathing slow. Let your thoughts drift apart like clouds separating on a summer afternoon. We begin. Part 1, The Idea of Darkness, Early Visions of Black Holes. Long before anyone had a telescope powerful enough to peer beyond our own galaxy, long before the word black hole existed in any language, human beings looked up at the night sky and felt, in the deepest part of themselves, that there was something out there beyond their understanding. Something ancient. Something vast. Something that pulled. The history of black holes is, in many ways, the history of human imagination reaching further than human instruments could follow. It is a story about what happens when a mind refuses to stop asking questions, even when the answers seem impossible. We need to begin in the year 1783. The world is a very different place. The American Revolution has only just concluded. Steam engines are beginning to reshape the English countryside. And a quiet English clergyman named John Michell is sitting in his study, working through the implications of Isaac Newton's theory of gravity. Michell was not a household name then, and he is not one now. He spent most of his life in Thornhill, a small village in Yorkshire, serving as a rector and pursuing science as a gentleman amateur. But he had one of the most remarkable minds of his era. He was the first person to propose that earthquakes travel in waves. He invented a device, later perfected by Henry Cavendish, that would be used to measure the gravitational constant of the Earth. He was, by any measure, a serious thinker. And in 1783, he presented a paper to the Royal Society of London containing an idea so radical that it would not be taken seriously for nearly 2 centuries. Michell reasoned from Newton's equations. Light, he knew, travels at a finite speed, approximately 186,000 miles per second, a number that had been estimated with reasonable accuracy since the 1670s. Gravity, he also knew, pulls on everything that has mass. And in Newton's universe, light was understood to be made of tiny particles, corpuscles, Newton called them, and if light had mass, then gravity should act on it. Michell asked a simple question: what if a star were massive enough that its gravitational pull exceeded the speed of light? What if a body were so dense that light, launched from its surface, could not escape? What if it would travel upward, slow, and fall back, the way a ball thrown into the air falls back to Earth? He called these objects dark stars. And he calculated, using nothing but Newton's mathematics, that such a star would need to have the same density as our Sun but be approximately 500 times larger in diameter. A star of that proportion, he said, would be invisible. This is a remarkable moment in the history of science. A man with a quill pen, sitting in a Yorkshire village in the 18th century, had just predicted the existence of what we now call black holes. He had done it using only the mathematics available to him, and he had gotten something deeply right, even if his reasoning, that light was made of Newtonian particles that gravity could slow, was, in some ways, wrong. The paper was noted by the Royal Society and then quietly set aside. The idea was simply too strange. Too far from anything anyone could observe or test. And when, a few decades later, the wave theory of light replaced the particle theory, Michel's reasoning seemed to fall apart entirely. Waves, the scientific community believed, were not subject to gravity. So dark stars seemed to be nothing more than a curious footnote. A French mathematician named Pierre-Simon Laplace had similar ideas around the same time, arriving at the same conclusion independently using very similar logic. He included calculations about these invisible bodies in his monumental work on celestial mechanics, published in 1796. But he too withdrew the idea in later editions as the wave theory of light gained ascendancy. And so the concept of the dark star went dormant, like a seed buried in winter soil, waiting for the right conditions to grow. Those conditions would not arrive for more than 100 years. They would arrive with the most revolutionary scientific idea in modern history. They would arrive with Albert Einstein. But before we reach Einstein, we need to spend a little time with the universe as it was understood in the late 19th century, a universe that seemed, to most scientists, to be essentially complete. A universe in which a few loose ends needed tidying up, but in which the fundamental laws were clear and settled. The physicist Albert Michelson, speaking in 1894, famously expressed the view that the great laws of physics had all been discovered, and that future advances in science would consist largely of measuring known quantities to a greater number of decimal places. The universe was, in his vision, a great machine, clockwork, predictable, essentially understood. He could not have been more wrong. The loose ends he and his colleagues were trying to tidy up were not loose ends at all. They were cracks in the foundation of everything. And through one of those cracks, the question of why the speed of light always appeared to be constant, regardless of how fast the observer was moving, Albert Einstein would push, and the entire edifice of classical physics would shudder and begin to transform. That transformation would eventually lead, through a long and winding path, to the prediction of black holes from within the framework of general relativity. It would lead to Karl Schwarzschild calculating the first black hole solution from a trench in World War I. It would lead to debates and dismissals and eventual confirmation. It would lead, ultimately, to the first photograph of a black hole's shadow, taken in 2019. But all of that is still to come. For now, let us simply rest in the image of John Michel, alone in his Yorkshire study, candle burning low, imagining a star so massive that light itself could not climb free of it. There is something beautiful about that image. A human mind, finite and mortal, reaching out across the dark and touching something real. Part 2. Einstein and the Bending of Space, the Theory of General Relativity. To understand black holes, we must first understand the framework from which they were born. And that framework is one of the most extraordinary intellectual achievements in all of human history, Albert Einstein's theory of general relativity, published in its final form in November of 1915. Einstein was 36 years old. He had already given the world the special theory of relativity, published a decade earlier in 1905, the same miraculous year in which he also explained the photoelectric effect and Brownian motion, 3 papers that would each, on their own, have been enough to secure a place in history. Special relativity told us something startling, that time and space are not absolute. That a clock moving quickly through space ticks more slowly than a stationary clock. That 2 observers moving at different speeds will disagree about whether 2 events happen simultaneously. That mass and energy are different forms of the same thing, connected by the famous equation E equals mc squared. But special relativity had a limitation. It dealt only with motion at constant velocity, what physicists call inertial motion. It said nothing about what happened when objects accelerated, and it was entirely silent on the subject of gravity. Einstein spent the next 10 years filling that silence. And what he produced was general relativity, a theory so beautiful, so strange, so deeply counterintuitive, that many of his contemporaries simply could not accept it. The central insight of general relativity is this: gravity is not a force. It is not a push or a pull acting between distant objects across empty space, as Newton had described it. Gravity is the curvature of spacetime itself. Let us sit with that for a moment. Einstein asked us to think of space and time not as separate, fixed stages on which events play out, but as a single, unified, flexible fabric, space-time. And he told us that mass curves this fabric. A star, a planet, any object with mass, creates a depression in the fabric of space-time, the way a heavy ball placed on a stretched rubber sheet creates a dip. Other objects moving through curved space-time follow the curves. The Earth orbits the Sun not because the Sun is pulling it with some invisible force across empty space, but because the Sun has curved spacetime around it, and the Earth is simply following the natural shape of that curved geometry. This is the deepest possible description of gravity, and it remains the best we have. And here is the crucial implication for our story: if spacetime can be curved by mass, then it can also be curved so severely, by a sufficiently massive and compact object, that it forms what we might imagine as a kind of drain, a region from which nothing, not even light, can escape. The mathematics of general relativity predicts this possibility with extraordinary precision. And the story of how that prediction was first extracted from Einstein's equations is itself a remarkable human story. It begins, of all places, on the Eastern Front of World War I. Karl Schwarzschild was a German physicist and astronomer, one of the leading astrophysicists of his era. He was also a man of fierce patriotism, and when war broke out in 1914, he volunteered for military service despite being over 40 years old. He served with the German army, first in Belgium, then in France, then on the brutal Eastern Front in Russia. It was there, in the winter of 1915 and 1916, calculating artillery trajectories and enduring the cold and the horror of the trenches, that Schwarzschild read Einstein's newly published papers on general relativity and began to work on them in his spare moments. The equations Einstein had published were extraordinarily complex, 10-coupled, nonlinear partial differential equations. Einstein himself had been forced to use approximations to solve them, believing that exact solutions might be impossible or at least very difficult to find. Schwarzschild found an exact solution in a matter of weeks. He considered the simplest possible case, a perfectly spherical, non-rotating object, with all its mass concentrated at a single point. He asked, "What does spacetime look like around such an object?" And he derived a precise mathematical description. His solution, now called the Schwarzschild metric, contained something deeply strange. At a particular distance from the central mass, the mathematics seemed to break down. The equations produced infinities, which in physics typically means something unusual is happening. This distance is now called the Schwarzschild radius, and the surface it defines is called the event horizon. Schwarzschild wrote up his findings and sent them to Einstein in December of 1915. Einstein was astonished. He presented Schwarzschild's paper to the Prussian Academy of Sciences with warm praise, calling it a first exact solution to his equations. Schwarzschild himself never saw what his solution would eventually mean. He contracted a painful autoimmune disease called pemphigus while serving on the Eastern Front and died in May of 1916, just months after making his great discovery. He was 42 years old. In the decades that followed, Schwarzschild's solution was studied and debated, but the strange breakdown in the mathematics at the Schwarzschild radius was generally regarded as a mathematical curiosity rather than a physical reality. Einstein himself believed that no real object could ever be compressed enough to reach its own Schwarzschild radius. The universe, he felt, would not permit such extremes. He was, in this instance, wrong. But we should not be too quick to move past Einstein's theory itself, because it deserves more of our attention. General relativity has been tested more rigorously than almost any other theory in the history of science, and it has passed every test. It predicted the precise bending of light around the Sun, confirmed dramatically during a solar eclipse in 1919. It predicted the precession of Mercury's orbit, a tiny wobble that Newton's equations could not account for. It predicted gravitational time dilation, the fact that clocks run more slowly in stronger gravitational fields, a phenomenon now confirmed with extraordinary precision and which must be accounted for in the GPS satellites that guide our navigation today. It predicted gravitational waves, ripples in the fabric of spacetime itself, spreading outward from violent cosmic events like rings on water. Those waves were finally detected in 2015, exactly a century after Einstein's theory was published. And most relevant to our story, it predicted black holes. The universe had been holding its secrets for billions of years. Einstein's equations, derived from pure thought, from mathematical beauty and physical intuition, had reached into the dark and found them. Part 3, The Collapse, How Stars Die and Black Holes Are Born. Stars are, in one sense, engines of opposition. For most of a star's life, two forces are locked in an eternal standoff. Gravity, relentless, patient, always pulling inward, is held at bay by the outward pressure of nuclear fusion. Deep in the core of every star, hydrogen nuclei are being crushed together with such force that they fuse into helium, releasing enormous amounts of energy in the process. That energy streams outward as radiation and heat, pushing against gravity, keeping the star inflated like a great glowing balloon. Our own sun has been burning in this way for about 4.5 billion years. It will continue for approximately another 5 billion years before its fuel begins to run out. But all fuel runs out eventually. What happens when a star's nuclear furnace begins to fade depends almost entirely on one thing: how much mass the star has. A star like our sun will swell into a red giant as its hydrogen runs low, puffing outward to perhaps 100 times its current size before eventually shedding its outer layers in a beautiful expanding shell called a planetary nebula. What remains at the center is a dense, hot, slowly cooling remnant called a white dwarf, a sphere roughly the size of Earth, packed with the mass of the sun, supported against further collapse not by nuclear fusion, but by a quantum mechanical effect called electron degeneracy pressure. Electron degeneracy pressure arises from a fundamental rule of quantum mechanics, the Pauli exclusion principle. This principle states that no two electrons can occupy the same quantum state simultaneously. As a white dwarf is compressed, its electrons are forced into ever higher energy states to avoid sharing the same quantum space, and this resistance creates a pressure that can, in many cases, hold the star up indefinitely. White dwarfs are stable objects. They cool slowly over billions of years and eventually, in the far future of the universe, fade to dark. They are stellar embers. But there is a limit to what electron degeneracy pressure can do. In 1930, a 19-year-old Indian physicist named Subramanian Chandrasekhar made a calculation that would reshape our understanding of stellar evolution. Chandrasekhar was aboard a ship traveling from India to England, on his way to begin graduate studies in Cambridge. He used the long weeks at sea to work through the mathematics of white dwarfs, incorporating the effects of special relativity. What he found was this: if a white dwarf has a mass greater than approximately 1.4 times the mass of the Sun, electron degeneracy pressure cannot hold it up. Gravity wins. The star collapses further. This number is now called the Chandrasekhar limit, and it is one of the most important figures in all of astrophysics. When Chandrasekhar presented his findings at the Royal Astronomical Society in London in 1935, he was met with public ridicule from the most famous astrophysicist in Britain, Arthur Eddington. Eddington declared that the result was absurd, that surely nature had some mechanism to prevent stars from collapsing in this way, that there must be some fundamental principle he was missing. He mocked the result in front of the assembled scientists. The humiliation was severe enough that Chandrasekhar, deeply wounded, shifted his research focus away from white dwarfs for decades. He would not receive the Nobel Prize for his discovery until 1983, nearly 50 years after he made it. But Chandrasekhar was right, and Eddington was wrong. For stars more massive than the Chandrasekhar limit, collapse continues beyond the white dwarf stage. As the core is squeezed further, the density becomes so extreme that electrons are forced to combine with protons, producing neutrons and releasing vast numbers of tiny, nearly massless particles called neutrinos. The collapse happens with catastrophic speed. The inner core of the star collapses from the size of Earth to the size of a city in less than a second. The infalling outer layers of the star hit this newly formed dense core and rebound in a titanic explosion. We call this event a supernova. For a brief period, a few weeks to a few months, a single supernova can outshine an entire galaxy of hundreds of billions of stars. It is among the most energetic events in the known universe. What remains at the center, if the original star was not too massive, is a neutron star, a sphere perhaps 12 miles in diameter, containing more mass than our Sun, composed almost entirely of densely packed neutrons. Neutron stars are held up by a quantum effect analogous to electron degeneracy pressure, neutron degeneracy pressure. They are among the strangest objects in the universe, spinning hundreds of times per second, generating magnetic fields trillions of times stronger than Earth's, with surfaces harder than any substance we know. But again, there is a limit. If the core left behind after the supernova has more than approximately 2 to 3 times the mass of the Sun, even neutron degeneracy pressure cannot withstand gravity. The collapse continues. And nothing, no quantum mechanical principle, no known force, can stop it. The core collapses to a point. Or something very close to a point. And a black hole is born. This process, the death of a massive star and the birth of a black hole, unfolds on a cosmic scale, but it also has a strange intimacy. Every atom in your body was once inside a star. The carbon in your bones, the iron in your blood, the oxygen in your lungs, all of it was forged in stellar furnaces and scattered across space in stellar explosions. We are, in the most literal sense, children of stars. And the black holes that form from dying stars are, in some sense, our most extreme kin. They are what stars leave behind when they finally surrender everything they have. The physicist Carl Sagan said it beautifully, we are a way for the cosmos to know itself. And black holes, strange and dark as they are a way for the cosmos to hide itself. To keep its deepest secrets in a vault from which nothing escapes. Part 4, The Event Horizon, where the universe ends. We have arrived at the event horizon. This is the boundary. This is the line in the fabric of spacetime beyond which nothing, no light, no matter, no signal of any kind, can ever return. It is not a physical surface, not a wall or a membrane you could touch. It is a mathematical boundary, a point of no return defined entirely by the geometry of curved spacetime. And yet it is one of the most significant boundaries in all of nature. The name event horizon was coined in 1969 by the American physicist Wolfgang Rindler, though the concept had been understood mathematically for decades before. The word horizon is apt, just as the horizon of the Earth marks the furthest point you can see, beyond which the surface curves away from view. The event horizon of a black hole marks the furthest boundary from which light can escape. Beyond it, the geometry of spacetime curves so severely that all paths lead inward. Let us think carefully about what this means. In ordinary space, if you want to move in a particular direction, you have options. You can choose to go north or south, up or down. You can choose to stay still. Your future includes many possibilities. But inside the event horizon of a black hole, something profound has changed. The crushing curvature of spacetime has altered the geometry so severely that every possible path through spacetime, every direction, every trajectory, leads toward the center. It is not that falling toward the singularity is one of your options. It is that falling toward the singularity is the only option. The future, for everything inside the event horizon, is the center. Physicists sometimes express this by saying that inside the event horizon, the radial direction, the direction toward the center of the black hole, has become time-like. It has taken on the character of time. Just as you cannot choose to move backward in time, you cannot choose to move away from the singularity. Both are simply impossible within the structure of that spacetime geometry. This is not a statement about technology or engineering. It is not that we lack a powerful enough rocket engine to escape. It is that the very geometry of the universe inside the event horizon makes escape impossible in principle. You would need to move faster than light, and that is something general relativity categorically forbids. Now, here is one of the most beautiful and disorienting facts about the event horizon. From the outside, falling through it looks nothing like the experience from the inside. Imagine watching a friend fall toward a black hole. As your friend approaches the event horizon, something extraordinary appears to happen. Gravitational time dilation becomes extreme near the event horizon. Time for your friend, from your perspective, appears to slow. Their movements become sluggish. The light coming from them becomes increasingly redshifted, stretched to longer and longer wavelengths, dimmer and dimmer. They appear to slow, to freeze, to hover at the boundary, growing dimmer and redder until they fade from view. But from your friend's perspective, the experience is entirely different. If the black hole is large enough, they might cross the event horizon without feeling anything unusual at all. There is no wall, no flash, no physical sensation at the moment of crossing. The tidal forces, the difference in gravitational pull between their head and their feet, might, for a very large black hole, be completely negligible at the event horizon. They would simply continue falling. Only later, falling deeper, would they realize that every path forward leads to the same destination. Only later would the tidal forces begin to grow. And this asymmetry, between what the outside observer sees and what the infalling observer experiences, is one of the deep puzzles of black hole physics. It leads to questions that are not yet fully resolved. It lies at the heart of what physicists call the black hole information paradox, which we will explore in its own time. The size of the event horizon depends on the mass of the black hole. Schwarzschild's formula gives the radius as a simple, elegant expression: 2 times Newton's gravitational constant times the mass of the black hole, divided by the speed of light squared. For a black hole with the mass of the Sun, the Schwarzschild radius is about 3 kilometers, roughly 2 miles. The entire mass of the Sun compressed into a sphere 3 kilometers across. For a black hole with the mass of a billion suns, the event horizon would be about 3 billion kilometers in radius, roughly the size of the orbit of Uranus around the Sun. These supermassive black holes, as we will discuss, lurk at the centers of most large galaxies, including our own Milky Way. There is something almost meditative about the event horizon. It is the most absolute boundary in the natural world. Not a wall but an absence, a place where the universe quietly folds itself away. On one side, the cosmos, with all its light and noise and possibility. On the other, a silence so complete that not even the idea of signal can cross back. The event horizon is, in a very real sense, the edge of the knowable universe. Not the edge in space, but the edge defined by information. Nothing that crosses it can ever tell us what lies beyond. Except, perhaps, through mathematics. And mathematics, it turns out, has things to say. Part 5, Inside the Singularity, where physics breaks down. Beyond the event horizon, falling deeper still, we approach something that general relativity predicts but cannot fully describe. The singularity. In the equations of general relativity, the singularity appears as a point, or more precisely, for a non-rotating black hole, a point at the center of the black hole where spacetime curvature becomes infinite, where density becomes infinite, where the laws of physics as we know them simply cease to function. The equations produce what mathematicians call a divergence, a point where quantities go to infinity, where the formulas spit out nonsense. Physicists have a saying about infinities in physical equations. They say, when an infinity appears, it means your theory has broken down. It means you have reached the limit of what your theory can describe. The singularity is precisely this kind of limit. It is the place where general relativity, our best theory of gravity, reaches its boundary and stops making sense. It is a signal that something is missing from our understanding, that we need a deeper theory, a more complete description of nature, to understand what truly happens at the center of a black hole. But let us first describe what general relativity does predict, before it reaches its limit. For a non-rotating black hole, the idealized Schwarzschild black hole, the singularity is not a point in space. This is a subtle and important point. It is a moment in time. Remember that inside the event horizon, the radial direction has become time-like. The singularity is therefore the future, the unavoidable end of all paths that lead inside the event horizon. It is the cosmic equivalent of tomorrow. You cannot avoid it simply by changing direction. As an object falls toward the singularity, it experiences what physicists call spaghettification. This wonderfully vivid term describes the effect of tidal forces on an infalling object. The gravity at your feet, slightly closer to the singularity, is stronger than the gravity at your head. This difference in gravitational pull stretches you along the radial direction while simultaneously compressing you from the sides. You are drawn out into a long, thin thread, like spaghetti. The effect grows without limit as you approach the singularity. For a stellar mass black hole, one formed from the collapse of a massive star, these tidal forces would be enormous even at the event horizon. An astronaut falling into such a black hole would be stretched and torn apart long before reaching the event horizon. They would never experience the interior. But for a supermassive black hole, one with billions of solar masses, the situation is different. The event horizon is so large that the tidal forces at the event horizon are relatively gentle, comparable, perhaps, to the tidal forces you experience on Earth from the Moon. An astronaut could cross the event horizon of a supermassive black hole without any immediate physical distress. Only later, falling deeper, would the tidal forces become lethal. But all paths, ultimately, lead to the singularity. Now, what does it mean, physically, for space-time curvature to become infinite? The most honest answer is, we don't know. We believe that general relativity is not the final word. At extremely small scales, at the Planck scale, where lengths are approximately 10 to the power of -35 meters, quantum mechanics must become important. At those scales, the smooth, continuous geometry of general relativity gives way to something we do not yet have a complete theory to describe. The leading candidate for a theory that might resolve the singularity is quantum gravity, a theoretical framework that would unify general relativity with quantum mechanics. String theory and loop quantum gravity are the two most developed approaches, but neither has yet produced a complete, agreed-upon description of what happens at the center of a black hole. Some theorists speculate that quantum gravity effects might smooth out the singularity, replacing the point of infinite density with a region of very high but finite density, a region small and strange, but not mathematically problematic. Others suggest more exotic possibilities, that the singularity is connected to another region of spacetime, perhaps even another universe. That the collapse of matter into a black hole might seed the birth of a new universe somewhere else. These ideas are, at present, speculation. Beautiful, mathematically motivated speculation, but speculation nonetheless. The Russian physicist Lev Landau once said that cosmologists are often in error but never in doubt. One might say something similar about those who theorize about the interiors of black holes. We are in the domain where imagination is necessary because observation is impossible, where the human mind must reach into the dark with mathematics alone. There is something humbling about the singularity. We have built rockets that have left the solar system. We have split the atom and sequenced the genome. We have mapped the cosmic microwave background radiation left over from the Big Bang. And yet at the center of a black hole, our best theories simply stop. The universe still has its secrets. The singularity is perhaps the deepest secret of all. And in that mystery, in that acknowledged limit of human knowledge, there is something strangely peaceful. We do not need to know everything tonight. Some things can simply rest in the unknown. Part 6, Types of Black Holes, From Small to Monstrous. Not all black holes are the same. The universe, in its infinite variety, has produced black holes across an astonishing range of scales. From the relatively modest remnants of collapsed massive stars, to the almost incomprehensibly large monsters lurking at the centers of galaxies, black holes come in types, each with their own character, their own physics, their own mysteries. Let us begin with the most familiar type, though familiar is perhaps a strange word to use for an object of such extremity. Stellar mass black holes are the direct products of stellar death. They form when massive stars, those with perhaps 8 or more times the mass of our Sun, complete their lives in supernova explosions, leaving behind cores that exceed the threshold for neutron star stability. The resulting black holes typically range from a few solar masses up to perhaps a few dozen solar masses. These are, in cosmic terms, relatively small objects. Their event horizons are measured in kilometers, not millions of kilometers. But small does not mean unimportant. Stellar mass black holes are, as far as we know, the most common type of black hole in the universe, and our own galaxy, the Milky Way, may contain hundreds of millions of them. Most stellar mass black holes are, by their nature, difficult to detect. A black hole alone in empty space, without nearby material to consume, is essentially invisible. It emits no light of its own, and its gravitational effects may be too subtle to notice without a nearby companion. But many stars form in binary systems, two stars orbiting each other. When one of those stars evolves and dies, leaving behind a black hole, its companion continues to orbit. And if the two are close enough, the black hole's gravity can begin to strip material from the companion star. This material forms an accretion disk, a swirling, spiraling disk of superheated gas orbiting the black hole, and as the material falls inward, it is compressed and heated to temperatures of millions of degrees, emitting powerful X-ray radiation. These X-ray binary systems were the first black hole candidates to be detected. The most famous is Cygnus X1, discovered in 1964 and identified as a likely black hole in the early 1970s. It lies about 6,000 light-years from Earth and contains a black hole of approximately 15 solar masses orbiting a blue supergiant star. The identification of Cygnus X1 as a black hole was famously the subject of a wager between the physicists Stephen Hawking and Kip Thorne. Hawking bet that it was not a black hole, Thorne bet that it was. The wager, a subscription to a magazine, was settled in 1990 when Hawking, acknowledging the accumulating evidence, conceded the bet. At the other end of the spectrum, we have supermassive black holes. These are the true giants of the universe, objects millions, or even billions, of times more massive than our Sun. They sit at the centers of virtually every large galaxy, and they are thought to play a crucial role in the evolution and structure of their host galaxies. The supermassive black hole at the center of our own Milky Way is called Sagittarius A*, pronounced Sagittarius A star. It has a mass of about 4 million solar masses and an event horizon about 12 million kilometers in diameter, roughly 17 times the diameter of the Sun. It lies about 26,000 light-years from Earth. The evidence for Sagittarius A*''s existence accumulated over decades of careful observation. Astronomers at the Max Planck Institute for Extraterrestrial Physics, led by Reinhard Genzel, and at the UCLA Galactic Center Group, led by Andrea Ghez, independently tracked the orbits of stars near the galactic center using infrared telescopes that could peer through the dust and gas obscuring that region of the sky. Over the course of more than 2 decades, they mapped the orbits of these stars with extraordinary precision. The results were unambiguous. The stars near the galactic center were orbiting something extremely massive and extremely compact, something with 4 million solar masses packed into a region smaller than our solar system. Only a supermassive black hole fit the description. Genzel and Ghez shared the Nobel Prize in Physics in 2020 for this discovery. But Sagittarius A*, as supermassive black holes go, is not especially remarkable. The black hole at the center of the Messier 87 galaxy, the one whose image was captured by the Event Horizon Telescope in 2019, has a mass of approximately 6.5 billion solar masses. Its event horizon is so large that it would encompass our entire solar system. And then there are the most extreme objects in the universe, ultramassive black holes, with masses exceeding tens of billions of solar masses, lurking at the centers of some of the most massive galaxies. TUN 618, a quasar, an extraordinarily luminous active galactic nucleus, contains a black hole with an estimated mass of 66 billion solar masses. Its event horizon would extend well beyond the orbit of Neptune in our own solar system. Between stellar mass black holes and supermassive ones, there is a puzzling gap. For decades, astronomers searched for intermediate mass black holes, objects with masses in the range of hundreds to tens of thousands of solar masses, and found very little evidence for them. This was puzzling, because if supermassive black holes grew from smaller seeds, there should be objects at intermediate masses. In recent years, evidence for intermediate mass black holes has begun to accumulate. Gravitational wave detectors have observed mergers of black holes with masses in the intermediate range. Observations of dense star clusters have revealed objects with masses consistent with intermediate black holes. The gap in our understanding is slowly closing. There is also a theoretical class of objects called primordial black holes. These, if they exist, would have formed not from stellar collapse but from density fluctuations in the very early universe, fractions of a second after the Big Bang. Depending on the conditions at the time of their formation, primordial black holes could in principle have any mass, from microscopic to very large. Some physicists have proposed that primordial black holes of a certain mass range could constitute part or all of the mysterious dark matter that makes up roughly 27% of the energy content of the universe. The search for primordial black holes is ongoing. We have not yet confirmed their existence. But the universe has surprised us before. What is clear is that black holes are not rare, exotic exceptions in the cosmos. They are, in some sense, ubiquitous. They are woven into the fabric of galactic structure. They are present in vast numbers throughout the universe. And they have been shaping the cosmos, bending the paths of stars, feeding on gas and dust, sometimes launching jets of material across millions of light years, for billions of years. Part 7, Hawking Radiation, When Black Holes Whisper. In 1974, Stephen Hawking made a discovery that astonished the physics world. He showed, using a combination of quantum mechanics and general relativity, that black holes are not entirely black. They glow. Very faintly, very coldly, but they glow. They emit radiation. This discovery, known as Hawking radiation, is widely considered one of the most important theoretical results in 20th century physics. And it carries within it a paradox so deep that it has occupied some of the greatest minds in physics for 50 years without resolution. To understand Hawking radiation, we need to first understand something about the quantum mechanical nature of empty space. In quantum mechanics, the vacuum, what we think of as empty space, is not truly empty. It is seething with activity, a restless foam of what are called virtual particles. These are particle-antiparticle pairs that spontaneously pop into existence from the energy of the vacuum itself. They exist for an incredibly brief moment, so brief that, under normal circumstances, they cannot be detected, and then they annihilate each other and disappear, returning their borrowed energy to the vacuum. This process, called vacuum fluctuations, is not a theoretical abstraction. It has real, measurable effects. The Casimir effect, for example, a tiny attractive force between two very closely spaced metal plates in a vacuum, is a direct consequence of vacuum fluctuations. It has been measured in laboratories. Now, consider what happens near the event horizon of a black hole. Hawking imagined that virtual particle pairs, spontaneously popping into existence just outside the event horizon, might occasionally be split apart by the boundary. One particle falls inside the event horizon, while the other escapes into space. The escaping particle becomes real, it is no longer virtual, because its partner has been swallowed by the black hole rather than being available to annihilate it. And the escaping particle carries energy away from the black hole. But where does that energy come from? It comes from the black hole itself. The infalling particle carries negative energy, energy borrowed from the black hole's gravitational field, and the net effect is that the black hole loses a tiny, tiny amount of mass with each such event. The radiation that the black hole emits in this way has a specific temperature, what we call the Hawking temperature. And here is something extraordinary: the Hawking temperature is inversely proportional to the mass of the black hole. A more massive black hole is colder. A less massive black hole is hotter. For the black holes that form from stellar collapse, the Hawking temperature is extraordinarily low, far colder than the cosmic microwave background radiation that fills all of space. These black holes are, in practice, absorbing more radiation from the universe than they emit, so they grow rather than shrink. But as a black hole loses mass through Hawking radiation, it becomes smaller and hotter, which makes it radiate more intensely, which causes it to lose mass faster, which makes it smaller and hotter still. The process accelerates. At the very end of its life, a black hole would radiate with explosive intensity, evaporating in a final burst of energy. For a black hole with the mass of our Sun, the time to completely evaporate through Hawking radiation would be approximately 2 × 10⁻�67 years, a number so incomprehensibly large that the universe would have to age many times over many times for such a black hole to evaporate. Even the most prodigious stellar mass black holes are, for all practical purposes, permanent on any timescale that has meaning to us. But Hawking radiation has implications far beyond the question of whether black holes eventually evaporate. It raises a question so fundamental that it strikes at the heart of our understanding of quantum mechanics: what happens to information? In quantum mechanics, information is sacred. The precise quantum state of a system, the complete description of every particle, every spin, every quantum number, is in principle conserved. If you know the current quantum state of a system, you can, in principle, calculate its past and its future. Information is never created or destroyed. This is called unitarity, and it is one of the foundational principles of quantum theory. But when a black hole evaporates through Hawking radiation, what happens to the information contained in the matter that fell in? Hawking's original calculation showed that the radiation emitted by a black hole is perfectly thermal. It is random, like the glow of a hot object, carrying no specific information about what fell in. A black hole formed from the collapse of hydrogen gas and a black hole formed from the collapse of a library of books, or a star, or a million different kinds of matter, would emit identical Hawking radiation. This means that when the black hole finally evaporates, the information about what formed it appears to be gone. Irretrievably gone. This is called the black hole information paradox, and it represents one of the deepest unresolved conflicts in theoretical physics. It sets the foundational principle of quantum mechanics against the implications of general relativity. Two of the most successful theories in the history of science cannot both be right, at least not in their naive forms. Hawking himself initially believed that information was truly destroyed by black holes, that quantum mechanics, in this respect, needed to be revised. He held this position for decades. But in 2004, at a famous conference in Dublin, he conceded that information was likely preserved after all, that the radiation emitted by black holes must carry subtle quantum correlations that encode the information about what fell in, even if we cannot practically decode it. The mechanism by which this happens remains deeply controversial and is an active area of research. Some physicists propose that information is encoded on the event horizon in the form of subtle imprints, microscopic marks left by infalling particles, recently dubbed soft hair by Hawking and his collaborators Malcolm Perry and Andrew Strominger. Others suggest that the resolution requires understanding the final moments of black hole evaporation, which lies beyond our current theories. And some physicists, most notably those working on what is called the firewall paradox, have proposed a dramatic possibility that the event horizon is not, as general relativity suggests, a benign boundary that a freely falling observer crosses without noticing. Instead, quantum mechanical effects might create a wall of intense radiation at the event horizon, a firewall, that incinerates anything that tries to cross. This would contradict a fundamental principle of general relativity called the equivalence principle, which says that a freely falling observer should not notice anything unusual when crossing the event horizon. If the firewall hypothesis is correct, one of our most deeply held principles of physics must be wrong. We do not know. Not yet. But the very existence of these questions, the fact that Hawking radiation forces us to confront the deepest contradictions between our two greatest physical theories, is itself a sign of progress. The universe is teaching us that we still have much to learn. Part 8, The First Image, Seeing the Shadow of Darkness. On April 10, 2019, at simultaneous press conferences held in Washington, D.C., Brussels, Santiago, Shanghai, Taipei, and Tokyo, an image was revealed to the world. It showed a glowing ring of orange and red light, bright on one side, slightly dimmer on the other, surrounding a dark central region. It was the first direct image of the shadow of a black hole. The image showed the black hole at the center of the Messier 87 galaxy, Messier 87 *, located 55 million light-years from Earth. The scale of what had been accomplished was staggering. The black hole's shadow subtended an angle of about 40 microarcseconds in the sky, about as large as an orange resting on the surface of the moon would appear from Earth. Imaging something so small, at such an enormous distance, required a telescope with a resolution far beyond anything a single observatory could achieve. The solution was breathtaking in its ambition, build a telescope the size of the Earth itself. The data collected during the observations in April 2017 filled 5 petabytes of storage, 5 million gigabytes. So much data that it had to be physically shipped on hard drives from some locations, because the internet connections were simply not fast enough to transmit it. The drives from the South Pole telescope had to wait months before they could even be retrieved, because winter in Antarctica makes air travel impossible. Processing and analyzing this mountain of data took nearly 2 years. The project was led by Shepard Dolman at the Harvard-Smithsonian Center for Astrophysics, and involved more than 200 scientists from 20 countries, working across many different institutions and collaborations. Among them was a young computer scientist named Katie Bauman, who developed crucial algorithms for combining and validating the data, and whose image, smiling broadly at her laptop as the black hole image appeared for the first time, became one of the iconic photographs of 2019. When the image was finally shown to the public, the reaction was unlike almost anything in the history of science communication. People who had never thought much about physics stopped and stared. This was not an artist's impression, not a computer simulation. This was a photograph, a real detection of real photons that had traveled 55 million light-years to reach our telescopes, bent and shaped by the gravity of an object so extreme that it had long seemed beyond human reach. The bright ring in the image is formed by hot plasma, superheated gas swirling in the accretion disk around the black hole. This plasma radiates intensely across a broad spectrum, including the radio frequencies that the Event Horizon Telescope was designed to detect. Some of this radiation travels on paths that curve tightly around the black hole before escaping. These are called photon orbits or the photon sphere, and the result is the distinctive glowing ring surrounding the dark central shadow. The bright ring is asymmetric, brighter on one side than the other. This is a consequence of the motion of the gas in the accretion disk. On one side, the gas is moving toward us, and its radiation is boosted by the Doppler effect. On the other side, the gas is moving away, and its radiation is dimmed. This effect, called Doppler beaming or relativistic beaming, is a direct fingerprint of the laws of special relativity operating in real time around a real black hole. The image was compared with predictions made from general relativity, and the match was extraordinary. The size of the shadow, the shape of the ring, the degree of asymmetry, all were consistent with the predictions of Einstein's theory applied to a black hole of 6.5 billion solar masses. General relativity, once again, passed the test with flying colors. In 2022, the Event Horizon Telescope collaboration released a second image, this one of Sagittarius A*, the black hole at the center of our own Milky Way. Imaging Sagittarius A* was in some ways more challenging than imaging the Messier 87 black hole, despite Sagittarius A* being much closer. Because it is much less massive, material orbits it far more quickly, causing the image to flicker and change on timescales of minutes, making it far harder to create a stable composite image. The result was nonetheless a triumph. A fuzzy, glowing ring, an orange donut shape, similar in form to the Messier 87 image, emerged from the data. There, in the center of our own galaxy, barely 26,000 light-years away, was the shadow of a 4 million solar mass black hole. It was our black hole. The one our galaxy orbits. The one that has been silently presiding over the Milky Way for billions of years. And we had taken its picture. These images matter beyond their scientific value. They matter because they change something in the human imagination. For all of human history, black holes existed only as mathematical abstractions, theoretical predictions, indirect inferences. Now they exist as images. As something you can look at. And that changes the relationship between the human mind and the cosmos in a way that is difficult to fully articulate. We saw the darkness surrounded by light. And somehow, the darkness had never seemed so real, or so beautiful. Part 9, Gravitational Waves, Listening to Black Hole Collisions. If the Event Horizon Telescope gave us eyes to see black holes, then gravitational wave detectors gave us ears to hear them. On September 14, 2015, at 5:51 in the morning Eastern Time, 2 detectors located in different parts of the United States, one in Livingston, Louisiana, and one in Hanford, Washington, simultaneously detected a signal. The signal lasted less than a second. It was a tiny vibration, a ripple in spacetime so small that the detectors, each with arms 4 kilometers long, moved by less than 1,000th the diameter of a proton. It was the first direct detection of gravitational waves. And it was the sound of two black holes colliding. The event, designated GW150914 after the date of detection, was the merger of two black holes located approximately 1.3 billion light-years from Earth. One had a mass of about 36 solar masses, the other had a mass of about 29 solar masses. They had been spiraling together for perhaps a billion years, losing energy as gravitational waves, moving faster and faster until, in their final fraction of a second, they were orbiting each other hundreds of times per second. In that final fraction of a second, the power radiated in gravitational waves was greater than the combined luminosity of all the stars in the observable universe. More power than all the light from 100 billion galaxies, compressed into less than a second. The two black holes merged into a single black hole of about 62 solar masses. The remaining 3 solar masses, more than 6 times the mass of the Sun, were converted entirely into gravitational wave energy and radiated away in that cosmic instant. The signal that reached Earth was a chirp, a brief, rising tone in frequency, increasing in pitch as the black holes spiraled together faster and faster. When this signal was converted into sound and played through speakers, it sounded eerily like a single, low thud. Brief, but unmistakable. The instruments that detected this signal are called LIGO, the Laser Interferometer Gravitational Wave Observatory. Their sensitivity is almost beyond comprehension. Each detector consists of 2 perpendicular arms, 4 kilometers long, down which laser beams travel. When a gravitational wave passes, it stretches one arm and compresses the other by a vanishingly small amount. The precision required to detect this stretching is equivalent to measuring the distance from Earth to the nearest star, Proxima Centauri, about 4 light-years, to an accuracy of less than the width of a human hair. Many physicists doubted it would work. The signals were so small, the sources of noise so numerous and varied, that detecting gravitational waves seemed to some like an impossible challenge. Every truck driving past the detector, every ocean wave breaking on the coast, every seismic tremor in the Earth, all of it could potentially mask or mimic a gravitational wave signal. The level of isolation and sensitivity required was extraordinary. But it worked. And since that first detection in 2015, LIGO and its European partner Virgo have detected many dozens of gravitational wave events, mergers of black holes, mergers of neutron stars, and mergers involving one of each. Every event is a window into the universe's most violent events, and every event tests general relativity in new and extreme ways. One detection in particular deserves special mention. In August of 2017, gravitational wave detectors detected the merger of 2 neutron stars. Unlike black hole mergers, neutron star mergers produce both gravitational waves and electromagnetic radiation. Astronomers around the world were alerted, and within hours, telescopes in space and on the ground were trained on the source. They detected a burst of gamma rays, then a fading glow across multiple wavelengths, then, in the days and weeks that followed, spectroscopic observations that confirmed something spectacular. The neutron star merger was producing heavy elements, gold, platinum, strontium, through a process called the R process, the rapid neutron capture process. Much of the gold in your jewelry, in the electronics that surround you, was forged in the violent death of 2 neutron stars spiraling together billions of years ago. The universe writes its history in the elements. The era of gravitational wave astronomy has opened an entirely new sense, a new way of perceiving the cosmos. For all of recorded history, we have known the universe primarily through light. Visible light first, then radio waves, then X-rays, then gamma rays and infrared and ultraviolet, all forms of electromagnetic radiation, all carried by photons. Gravitational waves are different in kind. They are not light. They are ripples in the fabric of space itself. They can penetrate anything. They travel through the universe almost completely unimpeded. And they carry information about events, black hole mergers, neutron-star collisions, that produce no light at all, or that occur in regions hidden from conventional telescopes. We have, in the past decade, grown new ears. And the universe is speaking. Part 10, Supermassive Black Holes and Galaxy Formation, the Cosmic Connection. Black holes, as we have discussed, come in a vast range of sizes. But the most influential black holes in the universe, the ones that have most profoundly shaped the cosmos we inhabit, are not the stellar mass remnants of individual dead stars. They are the supermassive black holes at the centers of galaxies. And the relationship between supermassive black holes and their host galaxies is one of the most fascinating and puzzling areas of modern astrophysics. Consider this remarkable fact: the mass of a supermassive black hole, across many different galaxies of many different sizes and types, correlates tightly with the mass of the bulge of its host galaxy, the central, roughly spherical region of stars that surrounds the galactic nucleus. This is called the M-sigma relation, and it is one of the most striking empirical regularities in all of extragalactic astronomy. More massive galaxy bulges contain more massive central black holes. And the ratio between the two is roughly constant. The black hole mass is typically about 0.5% of the bulge mass. This relationship holds across a range of black hole masses spanning several orders of magnitude, from millions to billions of solar masses. Why should this be? The galaxy bulge contains hundreds of billions of stars, spread across tens of thousands of light years. The black hole at its center, though enormously massive by everyday standards, occupies a volume that is tiny compared to the galaxy. How can something so small be so precisely related to something so large? The answer, astronomers believe, involves feedback. As a supermassive black hole feeds, as it consumes gas and dust from its surroundings, the infalling material releases enormous amounts of energy. Some of this energy drives powerful jets of plasma, streaming outward along the black hole's rotation axis at nearly the speed of light. These jets can extend for millions of light years, carrying energy far beyond the galaxy itself. But even within the galaxy, the energy released by an actively feeding black hole, we call such objects active galactic nuclei, or AGN, and the most extreme examples are quasars, can heat and drive away the gas that would otherwise continue forming new stars. This process, called AGN feedback, regulates star formation across the entire galaxy, linking the behavior of a compact, central black hole to the evolution of the vast stellar system surrounding it. In the early universe, quasars were far more common than they are today. The universe at 1 billion years of age was filled with brilliantly luminous quasars, black holes consuming gas at prodigious rates, outshining their entire host galaxies by factors of hundreds. Many of the brightest objects in the universe, visible across billions of light years, are quasars powered by supermassive black holes consuming the equivalent of many solar masses of material every year. The most distant quasars we have detected were shining when the universe was less than 1 billion years old. This poses a significant puzzle. How did black holes of several billion solar masses form in less than 1 billion years after the Big Bang? The universe was young, the first stars and galaxies had barely formed, and yet somehow, impossibly massive black holes already existed at the centers of the first galaxies. This is one of the most pressing unsolved problems in modern astrophysics. Several mechanisms have been proposed. Perhaps the first generation of massive stars, the so-called population 3 stars, formed from pristine hydrogen and helium with no heavy elements, were far more massive than stars today, and collapsed directly into black holes of thousands of solar masses, providing the seeds that grew to billions of solar masses through rapid accretion. Perhaps primordial black holes formed in the early universe served as the seeds. Perhaps the conditions of the early universe allowed gas to collapse directly into massive black holes without going through a stellar phase at all, a process called direct collapse. We do not yet know which, if any, of these mechanisms is correct. The James Webb Space Telescope, launched in December 2021 and now operating at an orbit around the second Lagrange point of the Earth-Sun system, is providing unprecedented views of the early universe. Its infrared sensitivity allows it to see galaxies forming when the universe was only a few 100 million years old, and among its many discoveries in its first years of operation have been unexpectedly massive and luminous galaxies at very high redshifts, objects that challenge our models of galaxy formation and that hint at active black holes operating even earlier in cosmic history than we had thought. The story of supermassive black holes and galaxies is, ultimately, the story of the universe itself. These massive objects did not simply form and then sit passively at the centers of galaxies. They interacted with their surroundings, shaped star formation, drove enormous outflows of gas, regulated the growth of galaxies, and then, as the available gas was depleted, they quieted down. The quasars faded. The AGN switched off. The black holes settled into relative quiescence. Our own Sagittarius A* is in this quiet phase. It is not currently feeding at any significant rate. It is an almost dormant beast, its appetite largely satisfied, its jets no longer blazing across the galaxy. Occasional small meals, a gas cloud drifting too close, a star torn apart by tidal forces, briefly stir it to activity. But for the most part, it sits quietly at the center of our galaxy, presiding in silence over 400 billion stars. The last major feeding event for Sagittarius A* may have been millions of years ago. But there are intriguing hints, structures of ionized gas called Fermi bubbles, extending tens of thousands of light-years above and below the galactic plane, that suggest it was far more active in the relatively recent cosmic past. We live in the galaxy's quiet age. And we owe the very structure of our civilization, perhaps, to that quiet. If Sagittarius A* were feeding actively, pouring out radiation and driving winds across the galaxy, life on Earth might never have had the stability it needed to evolve. We are here, in part, because our black hole is sleeping. Part 11, Rotating Black Holes and the Kerr Geometry, the Real Black Holes. We have spent much of our journey so far discussing the simplest kind of black hole, the spherically symmetric, non-rotating Schwarzschild black hole. This is the idealized case, the one easiest to calculate and describe, the one that Schwarzschild himself solved in the trenches of World War I. But the universe is not, in general, a place of perfect simplicity. Real stars rotate. And a rotating star, when it collapses to form a black hole, forms a rotating black hole. The rotation does not disappear when the black hole forms, it is preserved, because angular momentum is conserved. Indeed, as the collapsing star contracts, its rotation speeds up dramatically, just as a spinning ice skater spins faster when they pull their arms in. Rotating black holes are described not by the Schwarzschild metric but by the Kerr metric, derived in 1963 by the New Zealand mathematician Roy Kerr. Kerr's solution was found nearly 50 years after Schwarzschild's, and its discovery was greeted with excitement bordering on disbelief by the physics community. Kerr was working at the University of Texas at Austin, and he presented his solution at a meeting in Dallas in 1963. According to legend, his presentation was initially met with puzzlement and some skepticism. Einstein's equations are notoriously difficult to solve, and the idea that anyone had found an exact solution for a rotating mass seemed almost too good to be true. But the mathematics was undeniable, and within a few years the Kerr metric had become one of the most important results in all of general relativity. The Kerr geometry, the shape of spacetime around a rotating black hole, is far richer and stranger than the Schwarzschild geometry. Let us explore its most remarkable features. A rotating black hole drags spacetime around with it. This effect, called frame dragging or gravitomagnetic effects or, more formally, the Lense-Thirring effect, means that the very fabric of spacetime near a rotating black hole is in motion, spinning, swept along by the rotation of the black hole like water being dragged by a spinning drain. This frame dragging creates a region around the rotating black hole called the ergosphere. The ergosphere extends beyond the event horizon. It is a region outside the black hole proper, but within which spacetime is being dragged so strongly that it is impossible for any object to remain stationary relative to the distant universe. Everything inside the ergosphere, even light, is forced to rotate in the same direction as the black hole. The outer boundary of the ergosphere is called the static limit, and it is a remarkable surface. Inside it, you cannot hold still, no matter how powerful your rocket engine. The very fabric of space itself is moving, and you must move with it. But because the static limit lies outside the event horizon, it is still possible, in principle, to enter the ergosphere and then escape back into ordinary space. This leads to one of the most extraordinary theoretical results in black hole physics, the Penrose process. In 1969, the British physicist Roger Penrose, who would share the 2020 Nobel Prize in Physics with Genzel and Ghez, discovered that it is theoretically possible to extract energy from a rotating black hole using the ergosphere. The Penrose process works like this. An object enters the ergosphere and splits into two parts. One part falls through the event horizon, into the black hole, on a trajectory with negative energy relative to infinity. The other part escapes the ergosphere with more energy than the original object brought in. The net result is that energy has been extracted from the black hole, specifically from its rotational energy. The black hole slows down slightly. In principle, an extraordinarily advanced civilization could harvest energy from a rotating black hole in this way, extracting up to about 29% of the black hole's total mass energy. A rotating black hole also has a more complex interior structure than the Schwarzschild case. Instead of a point-like singularity, a rotating black hole, a Kerr black hole, contains a ring singularity. The singularity is a ring in the equatorial plane, and there are mathematically valid geodesics, paths through spacetime, that thread through the ring without touching the singularity. More extraordinarily, the Kerr geometry contains, inside the event horizon, a region called the inner horizon or Cauchy horizon. Beyond this Cauchy horizon, the mathematics suggests the existence of regions of spacetime that connect to other universes or to other regions of our own universe, structures called Kerr wormholes. In principle, the mathematics of the Kerr solution suggests that a traveler passing through the ring singularity could emerge into a different region of spacetime entirely, an anti-universe with different properties, or a separate region of our universe far removed from where they entered. These possibilities, wormholes, other universes, ring singularities, are among the most exotic predictions of general relativity. And they come with an important caveat. Physicists believe that the inner Cauchy horizon of a real Kerr black hole is likely unstable. The slightest perturbation, and real black holes are constantly being perturbed by infalling radiation, by quantum effects, by the imperfect conditions of actual astrophysical environments, would cause the Cauchy horizon to collapse into a strong singularity. The exotic interior geodesics that connect to other universes are, in all likelihood, blocked by this instability. This is a pattern we see repeatedly in black hole physics. The mathematics opens a door to something extraordinary. Closer inspection reveals that nature, in its wisdom, has placed a lock on that door. Roger Penrose formalized this intuition in what he called the cosmic censorship conjecture, the hypothesis that naked singularities, singularities not hidden behind an event horizon, cannot form in nature from reasonable initial conditions. And that the most exotic features of the interior geometry are shielded from outside observers by the event horizon itself. The cosmic censorship conjecture has not been proven mathematically. It remains one of the great open problems of classical general relativity. But it reflects a deep instinct shared by many physicists, that the universe, for all its strangeness, maintains a certain order. That it does not expose its most extreme features to casual inspection. Real astrophysical black holes are believed to be well described by the Kerr metric, or by the Kerr-Newman metric for black holes that also carry electrical charge. The no-hair theorem, proven by Werner Israel, Brandon Carter, Stephen Hawking, and David Robinson in the 1960s and 1970s, states that a classical black hole in equilibrium is completely characterized by just three numbers: its mass, its angular momentum, and its electric charge. Everything else, the composition of the material that formed it, the history of its formation, the detailed structure of any objects that fell in, is completely erased. This is the origin of John Wheeler's famous phrase, "Black holes have no hair." Every black hole with the same mass, spin, and charge is, classically, identical to every other. All information about its formation has been lost, or, according to the resolution of the information paradox that most physicists favor, encoded in the quantum state of the Hawking radiation it emits. The Kerr metric, in its full mathematical splendor, is one of the jewels of theoretical physics. It describes objects that are real, actually out there in the universe, spinning at some fraction of their maximum possible rotation rate, dragging space around them, harboring exotic inner structures. Every stellar mass black hole formed by a collapsing, rotating star is a Kerr black hole. Sagittarius A** is a Kerr black hole. Messier 87* is a Kerr black hole. The universe is populated with Kerr geometry, and Roy Kerr's 1963 solution, found not from any astronomical observation but from pure mathematical analysis of Einstein's equations, describes it perfectly. There is something deeply moving about this. A mathematician, working alone at his desk in Texas in 1963, found an exact mathematical description of objects that were then entirely theoretical and that would not be observationally confirmed for decades. He reached into the equations and pulled out the shape of something real. Mathematics is, in this sense, one of the great mysteries of science. Why should abstract mathematical structures, invented by human minds without any reference to the physical world, so precisely describe that physical world? Eugene Wigner called it the unreasonable effectiveness of mathematics in the natural sciences. And nowhere is this unreasonable effectiveness more striking than in black hole physics, where the most exotic features of real astrophysical objects were first glimpsed not through telescopes, but through equations. Part 12, The Future of Black Hole Science, What We Still Don't Know. We have traveled far tonight. From John Michell's candlelit study in Yorkshire, to Einstein's equations of curved spacetime, to Schwarzschild's trenches on the Eastern Front, to the death of stars and the birth of black holes, to the event horizon and the singularity, to Hawking radiation and the information paradox, to the first image of a black hole's shadow and the first sound of two black holes merging. We have traced the full arc of one of science's greatest stories. And yet we stand, at the end of all this, at the edge of a vast ocean of unknowing. The questions that remain open in black hole physics are not peripheral questions, not matters of fine detail. They are central, foundational, fundamental. They concern the deepest structure of space and time. They concern the nature of information and quantum mechanics. They concern the beginning and ending of the universe itself. And they are, as yet, unanswered. Let us spend some time with these open questions. Because the frontier of science is, in many ways, the most interesting place to be. The most urgent unresolved question in black hole physics, and perhaps in all of theoretical physics, remains the information paradox. We touched on it when discussing Hawking radiation, but its implications run deeper still. The paradox, at its heart, is this: quantum mechanics requires that information is never destroyed. General relativity, combined with Hawking's calculation, suggests that black holes destroy information. Both cannot be right. Something in our understanding must give way. In recent years, remarkable progress has been made on this question using tools from a branch of mathematics connecting quantum gravity to quantum information theory, centered on a principle called the holographic principle and its most concrete realization, the AD/CFT correspondence. The holographic principle, first proposed by Gerard T. Hooft and further developed by Leonard Susskind in the 1990s, suggests that the information content of a region of space is encoded not in its volume, but on its boundary surface, in 2 dimensions rather than 3. A 3-dimensional region of space is, in this picture, like a hologram. The full 3-dimensional information is encoded in a 2-dimensional surface. The AD/CFT correspondence, discovered by Juan Meldacena in 1997, is the most concrete realization of this principle. It relates a theory of gravity in a particular kind of spacetime, anti-de Sitter space, to a quantum field theory living on the boundary of that spacetime, with no gravity. The two theories are exactly equivalent. Any calculation in one can, in principle, be translated to a calculation in the other. Within this framework, black holes can be described in terms of the boundary quantum field theory. And in the boundary theory, time evolution is unitary, information is preserved. This strongly suggests that information is indeed preserved in black hole physics, and that Hawking's original calculation missed something, some subtle quantum correlations in the radiation that carry the information away. In 2019 and 2020, two groups of physicists independently calculated what is called the Page curve for black hole evaporation, a curve that describes how the entanglement entropy of the emitted radiation changes over time. The Page curve, predicted by physicist Don Page in 1993, shows that the entropy should initially increase, then decrease as the black hole finishes evaporating, returning to zero when all information has been emitted. Using techniques from the holographic correspondence, these groups recovered the Page curve from gravitational calculations for the first time. This was a significant breakthrough. It strongly suggests that information is preserved in black hole evaporation. But it does not yet tell us precisely how. What is the physical mechanism by which the information escapes? This remains an active and exciting area of research. A second great open question concerns the singularity. We know that the singularity at the center of a black hole signals the breakdown of general relativity. We know that a quantum theory of gravity is needed to describe what truly happens there. But we do not yet have a complete, agreed-upon quantum theory of gravity. String theory, which treats the fundamental constituents of matter not as point-like particles but as tiny vibrating strings, and which requires extra dimensions of space beyond the familiar three, has produced many beautiful results in black hole physics. It provided the first statistical mechanical explanation of black hole entropy, derived by Andrew Strominger and Kamran Vafa in 1996 using string theory techniques, showing that the entropy of certain special black holes could be understood as arising from the number of microscopic quantum states available to the system. This was a profound confirmation that Hawking's thermodynamic description of black holes has a genuine quantum mechanical underpinning. Loop quantum gravity, an alternative approach to quantizing gravity that does not require extra dimensions, makes different predictions. In loop quantum gravity, space itself is quantized. It comes in discrete chunks at the Planck scale, rather than being continuous. Within this framework, the singularity at the center of a black hole is replaced by a quantum bounce, a region of very high but finite density where the collapsing matter bounces back, perhaps seeding a new region of expanding spacetime. Some versions of this idea suggest that black holes might give birth to new universes in a process called cosmic inflation on the inside. These are beautiful ideas. They are also, at present, largely untestable. The quantum effects they predict occur at scales so small and in conditions so extreme that we have no foreseeable way to observe them directly. But the situation may not be hopeless. Gravitational wave astronomy is producing new tests of general relativity in the extreme gravity regime every year. Future gravitational wave detectors, LISA, the space-based interferometer planned by the European Space Agency for launch in the 2030s, the Einstein telescope, Cosmic Explorer, will detect gravitational waves from black hole mergers with far greater sensitivity, probing the geometry of spacetime near the event horizon with unprecedented precision. The Event Horizon Telescope collaboration plans to continue improving the resolution and sensitivity of its observations, eventually creating images of black holes with enough detail to see not just the shadow, but specific features of the photon ring, the nested subrings of light created by photons that have orbited the black hole multiple times before escaping. The structure of these subrings encodes precise information about the geometry of spacetime near the event horizon, providing potential tests of the Kerr metric and, if deviations are found, hints toward new physics. Pulsar timing arrays, networks of millisecond pulsars used as cosmic clocks, have recently detected what appears to be a background of gravitational waves permeating the universe, likely produced by the mergers of supermassive black hole pairs throughout cosmic history. This gravitational wave background is a new observational window into the population of supermassive black holes and their mergers, complementing both the LIGO observations and the Event Horizon Telescope. And the James Webb Space Telescope continues to push back the frontier of what we know about the early universe, revealing galaxies and black holes at redshifts that challenge our existing models, forcing us to revise our understanding of how quickly structures could form in the young universe. There is also the deep question of what lies beyond the event horizon, not just at the singularity, but in the entire interior. We have never observed the interior of a black hole, and given the causal structure of the event horizon, we never can, at least not from outside. Any information about the interior, once crossing the event horizon, is forever inaccessible to the rest of the universe. This is not a limitation of our technology. It is a fundamental constraint imposed by the geometry of spacetime. And yet the mathematics speaks. The equations of general relativity describe a rich interior geometry. The equations of quantum mechanics suggest that information about this interior is somehow preserved and encoded in the exterior. The holographic principle suggests that the full description of everything inside the event horizon is somehow contained in the boundary. Perhaps the most profound thing about black holes is not any specific feature, not the event horizon, not the singularity, not the Hawking radiation, but what they represent philosophically. They are the places where the universe enforces its most absolute limits. They are the points where our theories reach their boundaries. They are the objects that connect our largest scale understanding of gravity to our smallest scale understanding of quantum mechanics. They are, in a very real sense, the proving ground for the next great theory of physics. Every major advance in physics has required a willingness to abandon previously comfortable assumptions. Newton showed that the same force that pulls an apple from a tree also keeps the moon in its orbit, a profound unification that required abandoning the distinction between earthly and heavenly physics. Einstein showed that space and time are not the fixed, absolute stage on which physics plays out, but dynamic, flexible participants in the drama, a revolution that required abandoning the most deeply held intuitions about the nature of reality. Quantum mechanics showed that at the deepest level, the universe is not deterministic, that particles do not have definite positions and momenta until they are measured, a revelation so strange that Einstein himself never fully accepted it. The quantum theory of gravity, whatever form it takes, will almost certainly require equally radical revisions. It may require abandoning our notion of spacetime as a fundamental entity, deriving it instead from something deeper, something more quantum mechanical. It may require accepting that what we call space and time are emergent phenomena, not fundamental ones, that they arise from more fundamental relationships, the way temperature arises from the collective behavior of many atoms, none of which individually has temperature. Black holes are pointing the way. Their paradoxes and puzzles are not failures of understanding but invitations. They are the universe saying, "Look here. This is where the old understanding breaks down. This is where the new understanding begins." And we are, right now, at one of the most extraordinary moments in the history of this investigation. Gravitational wave detectors are operating. Space telescopes are seeing the early universe. Radio telescopes networked across the Earth have photographed the shadows of black holes. Theoretical physicists are making genuine progress on the information paradox. The quantum gravity programs are maturing. We may be within decades, perhaps a generation, perhaps two, of a genuine breakthrough in our understanding of what black holes truly are, and what they tell us about the deepest nature of reality. The history of science is, at its best, a love story. It is the story of human beings falling in love with the universe, with its complexity, its beauty, its mystery. It is the story of minds reaching beyond what is known, with nothing but curiosity and the willingness to follow an argument wherever it leads, even when it leads to places that seem impossible. John Michell, imagining a dark star in Yorkshire in 1783. Karl Schwarzschild, finding an exact solution to Einstein's equations in a trench in Russia in 1915, months before his death. Subramanian Chandrasekhar, calculating the limit of stellar stability aboard a ship crossing the Indian Ocean. Roy Kerr, finding the geometry of rotating black holes at his desk in Texas. Stephen Hawking, deriving that black holes glow, that the darkest objects in the universe whisper faint thermal radiation into the surrounding cosmos. Kip Thorne, Rainer Weiss, and hundreds of colleagues, spending decades building instruments of incomprehensible sensitivity to catch the vibrations of distant collisions. Katie Bauman and 200 scientists, weaving together radio waves from telescopes on every continent to produce the first photograph of a black hole's shadow. These are human beings. Finite, mortal, limited, just like us. They looked at the dark and found light. They held questions that seemed unanswerable and answered them. They built, from mathematics and metal and human ingenuity, windows onto the most extreme corners of the universe. And the work continues. Tonight, somewhere in the world, a young physicist is staring at equations describing the interior of a black hole, following the mathematics wherever it leads. Somewhere, a graduate student is writing code to process gravitational wave data from the latest black hole merger. Somewhere, a radio astronomer is planning observations that will sharpen the images of Sagittarius A** and deepen our understanding of the black hole at the center of our own galaxy. The story is not finished. It is, in the most beautiful sense, just beginning. Closing meditation. We have traveled far tonight. From the early inklings of dark stars in a candlelit study, through the revolution of curved spacetime, through the birth and death of stars, through the absolute boundary of the event horizon and the mystery beyond it. Through the faint whisper of Hawking radiation, through the first photograph of light bent around an abyss 55 million light-years away, through the sound of two black holes finding each other across a billion years of spiraling and finally merging in a fraction of a second. And now we come to rest. The universe is very large, and it is very old, and it holds its deepest secrets in the darkest places. But it is not indifferent to us. We are made of it. Every atom in your body was forged in a star. The iron in your blood carries the history of supernova explosions that happened billions of years before the Earth was born. And you are here, now, resting quietly, breathing slowly, your mind drifting gently through the space between wakefulness and sleep. The black holes we have visited tonight are still there, still spinning, still bending light, still whispering faintly into the quantum vacuum. Sagittarius A** is still sitting quietly at the center of our galaxy, 26,000 light-years away, patient and immense and dark. And you are here. Small, warm, alive. A part of the universe that has learned to wonder about itself. Let that wonder settle over you like a blanket. Let the questions rest. There is nothing to solve tonight. The universe will keep its secrets a little longer, and that is all right. You are safe. You are resting. And the cosmos, with all its black holes and dying stars and gravitational waves and curved spacetime, wraps around you like the dark and holds you gently as you sleep. Good night. If you're still awake, the universe is vast and full of wonder. Subscribe to Cosmos and Dreams for a new discovery every week. Sweet dreams.